Hello, everyone. Welcome to ACMAI's Advanced Track Workshop for Winter 23. If you want the slides and to be able to follow along, and if we're going through too quickly, the slides linked are here. It says Fall 22, but it's the same link. And the feedback form also says Fall 22 because you can tell we're very, very prepared. But if you just fill in whatever feedback you have here, we will still be able to get it because we still have access to Excel spreadsheets. So just don't worry about it if it says Fall 2022. So this is going to be the workshop where we dive in a little bit deeper into machine learning. Like some of you here may have done beginner track. Actually, can I see a raise of hands of those who have done beginner track here? Okay, so we have a few people. No, that's totally okay. And I'm assuming that the rest of you have like a little bit of knowledge of what machine learning is, some idea of it, a little bit of experience in Python or something like that, right? And again, if you don't, that is totally okay. Like again, beginner track is obviously an option. They run every Tuesday in Haynes something. I gotta check, but in Haynes from 6 to 7:30. If you feel like this is a bit too much for you, and after all, they will still just be on their second meetings. So that is good. However, if you're here, definitely just kind of sit for this whole thing and then just have a listen to see if this is right for you. And don't be afraid to just kind of raise your hand or even just shout out any questions if you have anything in the middle like that. Let's delve into machine learning. So, this is my picture's gonna load. Great. There we go. I did something. Anyway, so this is us.
Okay, so my name is Preetham Pangaluru, shown on the screen. The colors are different, so I like it that way. But I'm a computer science major, and I'm a third year.
I'm Gordon Lin, and I am a second-year computer science major.
I'm Oscar. I'm a first-year comp sci major.
Yeah, and Angeline will not be able to be here today, but you will be able to see her in the future because she's also going to teach some content here and there. So today's topic is feed-forward neural networks and stochastic gradient descent. And if you don't know what it is, well, you have come to the right place because this is kind of like the foundation of neural networks and machine learning. This is kind of what you will be dealing with in the future, whether you're going to be doing, computer vision, natural language processing, or any tasks that has to do it's kind of like these kind of hot research topics nowadays. You can kind of think of this workshop as a sort of companion/condensed version of a lot of kind of popular UCLA machine learning courses like CSM 146 or ECEC 147. We don't cover all of the topics, of course, because we have much less time, but then we try to give you a much more hands-on approach. So week 1 to 5 will be kind of more theory-based, where we tell you different, we cover things like, feed-forward neural networks, convolutional neural networks, recurrent neural networks, and kind of like a little bit of introduction to PyTorch and backward propagation. And weeks 6 to 7 will be the time where we actually give you something called Jupyter Notebooks, which we'll cover what that is in the future. And you will be able to hands-on create your own image classifier from scratch, which I think is pretty exciting. So yeah, let's begin with the first workshop. So this is just kind of quick table contents. And again, for those of you who just joined, I will kind of put up the slides. Once again, this is the link to the slides, tinyurl.com AI-advanced ADV F22-1. Just gonna leave it up there for 5 more seconds. Everyone go with that? Cool. All right. So let's start with we'll always say quick review, but again, if you have questions, feel free to just kind of ask, right? So let's begin with something I think is kind of almost like the hello world, or like the one thing you have to talk about for machine learning. But before we begin with anything more complex, logistic regression. Oscar?
So first we'll talk about logistic regression. We use logistic regression in machine learning to do classification tasks. So for example, we want to see if the animal in the image is a cat or a dog, or if the patient has a cancer or not, based on the image. So to do this, we need our model to give us a probability value. So basically, we need a number between 0 and 1. So the problem is, if we just use our good old linear functions, we cannot get a value between 0 and 1, because, well, our linear function would just take our input and then map it to any number between negative infinity and positive infinity. And as you can see from the graph, like it just like spans from this end to the other end. And we can't use that to make a probabilistic prediction. So how do we fix this? Well, easy. We just use the sigmoid function, which is defined as 1 over 1 plus e to the power of negative x. So if we look at this function closely, you can see that when x is equals to 0, our function is equals to 1 over 2, which is 0.5. And in fact, all the changes in this function will either increase from 0.5 or decrease from 0.5. So specifically, when x is a negative number, because our denominator will become bigger and bigger, our value will actually be less than 0.5. And it will continues to get lower until it approaches 0. On the other hand, if x is a positive number, our denominator will become less and less. So our value will become greater than 0.5 and continues to get greater until it approaches 1. One key thing to note that is this function has a range between 0 and 1, and it's not inclusive. So that means our function will never be 0 nor 1. And if you look at this graph, you can see how it plays in the role of classification. So suppose that today we want to create a machine that tells you whether like the animal in the image is a cat or not. So if in the end, our computer model gives a value of 2, and then according to a sigmoid function, it's about like 0.8. So the model can look at this number and say, well, we have a probability of 0.8 that the animal in this image is a cat. So therefore, it concludes that it is a cat. However, today, if the model gives like -2, and if we map it into the sigmoid function, it's like 0.2 or something. So, and then the model will say, well, like the probability of this animal being a cat is just 0.2. So it's probably not a cat. So it will conclude that, well, this animal is indeed not a cat. And there you go. We have our classification task done based on probability using the sigmoid function. Any questions so far?
So you can think of the sigmoid function as a sort of thing that's kind of limiting the range of the output of our function, such that instead of it kind of just extending it all the way out to infinity, when we take like the really big ends, like the really positive ends, and the really negative ends, we're kind of just kind of tapering it off, kind of pushing it so it's between the range of 0 and 1. And that can be very helpful because with something like with something like logistic regression, whenever we have an output, we often want to limit it because then what happens is we're instead modeling something like probability, right? And modeling probability, it has been shown that it's actually something that's much more helpful for us to be able to actually do classification because the intermediate values actually does mean something. And there's another reason. So this sort of function you will see is something called activation functions. And the reason for having these sort of functions is also to what we'll call something called limiting the kind of magnitude or size of something called the gradient, which we'll learn a bit later. But like the thing about machine learning is because we're going to be dealing with so many numbers, having something that allows us to limit the magnitude or limit the sort of size of our outputs is always very, very helpful. So just kind of keep that in mind. Keep that in the back of your head for now.
Also, adding on to the example of like whether a picture or like an image is a cat or not, I just want to clarify that the sigmoid function is like binary classification. So while this example is correct, I just want to put it out there that like it's only 2 classes. So it'd be like cat and non-cat. But we're going to probably see it in a later workshop or today about something that classifies many like classes. So.
Next, we'll talk about optimizers. So, well, obviously, when you're first designing a model, it's pretty impossible for like your model to run perfectly with your given like weights and biases. So, like in fact, it probably like it is pretty common that your model will perform like terribly the first time you run it. So, but then how does like a computer know how well our model has performed? Well, we have a loss function. So the loss value is basically an evaluation of how well our model has performed compared to our expected outcome. So that means the higher the loss value, the worse our model is performing. So our goal is to try to lower, to minimize our loss value as much as possible. So this is where our optimizers come in. So optimizers, basically, they try to lower our model's loss by adjusting the weights for our models. And our hope is that by like changing and like nudging these values for our weights, like our models can have the minimum loss and like perform as best as they could.
And if you're wondering what the loss really is it takes the output of a model and it says, okay, we have this output of this model and we compare it to the ground truth, or like what we want the model to output. It takes those two things and it does some math to it. We'll kind of get into those math a little bit later, but it does some math to it and it gives you one value, one scalar. And that one singular scalar tells you how good the model is doing. And in this case, it's kind of counterintuitive, but the lower this value is, the better the model is doing, because it's kind of measuring the error of the model. So basically, we kind of have this kind of like whole pipeline of like, you know, inputs to outputs, and then you put in the label to loss, and you kind of have this like massive function. And you guys know what functions are, right? So you have this massive function that you're trying to optimize. You're trying to nudge the model's weights around. The weights are the things that actually take the input and manipulate it in such a way that we get the outputs. You're trying to manipulate those such that you're trying to get to the lowest loss. So that's kind of the idea of optimization, the optimization problem, if you will.
So we can visualize it with a loss landscape. So suppose that today we have a model with two weights. So we have a vector W with like two components, W1 and W2. And then we have a loss function that is dependent on these two vectors. This vector. And then we can plot our loss function with respect to our vector. And then we'll have a 3D graph, which looks like these. And we call it the loss landscape. So our goal is to find a point on this landscape that such that our loss value is at its global minimum, or at least a good local minimum. Because when it's at its lowest point, we know that it makes the minimal amount of error. So, well, of course, this is the loss landscape is not limited to like 2D vectors. And in fact, like most models have more than two weights, like it has hundreds and thousands of weights. So the vector gets really complicated. But the thing is, like, our brain can't really process like images in like higher dimensions. So like when we're like giving the example or just visualizing it, we only use two vectors and with the loss function, so that creates a 3D graph. And now the question is, how do we find a good minimum? So, well, it's simple and easy if you just like look at the graph and you can point out, oh, okay, see, so this is the lowest point. But then a computer cannot do that. They don't have eyes. They don't have like intuition to tell them like, oh, this is the lowest point. So the way that we teach computers to find a good minimum is our next topic.
Okay, so let's talk about something that's very, that is kind of like at the core of optimization for neural networks. This is how a machine learning model can go from what is essentially random initialization and be able to learn from data. Because after all, machine learning is really a process of, especially specifically for neural networks, it is a sort of what we call data-driven approach, right? It is a sort of learning algorithm or that is based on us giving it a bunch of examples and trying to figure out what is the best way for us to present that. And we use something called gradient descent. With most methods nowadays, like if you've heard of optimizer names, like for those of you who are a little bit, prolific in here, like, Atom, RMS prop, whatever, they're all variants of something called gradient descent. So let's look at our kind of 2D weights example again. So our 2D weights example, the weights can really be represented as a little like vector of two values, if you can think about it. We think of like this is like vector 1, W1, this is W2, something like that, right? And our goal is to find the direction in which the slope of the loss landscape is the most negative. I want to let that sink in a little bit. We want to find the direction in which the slope of the loss landscape is the most negative. And we want to iteratively nudge W in that direction. Now, who here has taken Math 32A? Did you like that class? I see those begrudging, I don't know how to respond to this, but there may be one concept in Math 32A that you may remember. When we have a multivariable function, what is the direction of greatest ascent? Does anyone have any answer to that?
Gradient.
The gradient, that is correct. So, but what is the gradient? So, what the gradient is it is the way mathematicians like to put it, the partial derivative of the final output with respect to each dimension of the input. And what that is basically, if you think about it, if you look back at what really neural network is, we have a function, right? It takes two inputs, in this case, our first weight and our second weight. And if you think about it, you're like, wait, but what about our image? We got to put the image in as well, right? Well, the thing is, when we're putting in the image, we're putting in different images every time. And that's kind of changing the nature of the function. However, what we are really changing, the thing that we are changing and the thing that we're nudging around, we're learning, is the network weights. That is the things that is affecting how, when we give it an image, the output that it gives us at the very end. And because of that reason, we have this kind of function, right? We envision this whole model, this whole neural network model from, giving it our weights and obviously our image all the way to getting the loss as one function. And we're saying, let's take the partial derivative of the loss with respect to each and every single one of the weights, right? Because if you envision our loss landscape, what that's really saying is we're trying to find the direction in which you can imagine our current model as a point in the loss landscape. It's a random initialization because it has that sort of random value in every single one of the weights. And we're saying, how do we move this point around such that we reach a minimum? Because if we reach the minimum, that means we have found some way of determining what these weights are such that our loss will be minimized. And if G, or a gradient, is the direction of greatest ascent, it is the direction in which we move this point at this very current instance such that we can make the loss as big as possible. If we go in the opposite direction, then we're making the loss as small as possible, at least for this very instance. Does that make sense what's happening here? It's like thumbs up, kind of confused. I have no idea what's going on. Okay, I'm seeing mostly thumbs ups, a few confusions, but if you look at this animation, that's kind of what's happening. When we're at this very top point, the direction of greatest descent is going this direction, right? Because the direction of greatest descent will be going up here somewhere. So we do this kind of iterative process, and eventually we're going to reach some sort of minimum. And that's kind of the goal here, because with something as complex as neural networks, when we have thousands, even billions of parameters, it is often impossible to find some sort of very direct solution for us to say, oh, this is where we can get the best possible model. That's just not very realistic. That is why optimization is the whole field of study. And this is why we want to say, let's do this iteratively, and we just want to find some sort of minimum. That's good enough, right? It's low enough, we're happy with it. That's why we never really say global minimum. We just say a good local minimum. Does that make sense?
Yeah, extending on that,
Yeah.
like the function may not be as simple as this. So like it could be like, what p, and like I guess we have an example here as well. So like these are all local minima, but like, getting one of those is like the ideal solution, but there's like no global minima, or even if there is, we don't necessarily know if we could reach it. So gradient descent sort of helps us minimize, but we can't necessarily always guarantee we get to the global minimum. So. And another thing I wanted to point out is like the direction of like gradient descent may not be like, I guess it's changing, but as time goes on, like the change is like smaller and smaller until it reaches like the minimum, which is also worth noting. Yes. Yeah.
Oh, there we go. Do y'all remember how to do partial derivatives? We're not really actually making it do this, but like this is kind of what a neural network is trying to do every time it's trying to compute the gradients. Basically, if we have, we have like really simple functions like this, and we can try to compute, the partial derivatives of each of the output with respect to each of the inputs. And if you think about kind of these two values, we can kind of group them together to make a vector, and that will be kind of our gradients of this function in this case. Right. And again, this may look really daunting. And the really great thing about modern machine learning is that a lot of the Python packages kind of just does this for you. But we think it's very helpful to understand what's going on behind these packages, because then you are really confident with the choices that you're making. Right. So next slide.
Oh, yeah, you don't want to go over it.
Yeah, I think it's fine, right? Right. So now here's one problem. The gradient kind of seems hard to calculate. Again, imagine we have this kind of huge network, huge neural network that takes in this relatively big image and just gives us some sort of outputs. And we may have some code that outlines how this is done. But how do computers know what is going on inside an arbitrary machine learning model? Has anyone heard of the term of machine learning models are like black boxes? Is that something that yeah, some of you may have heard of that, right? And yes, to a user, it may look like a black box. But the one thing about machine learning, when we as perhaps machine learning scientists, do a lot of these stuff, is we have control over what's happening at each layer. And we know what's happening inside. We may not know how to interpret what the model is doing, but we know what's inside. So it does feel like a black box model, but there is a way to compute the gradients. And in this case, the simplified explanation is PyTorch does it for us in the presentation. I'm just kidding. But the idea is the computer has ways of calculating the gradients via something called backwards propagation, which is really just a fancy way to say chain rules go blur, right? But we're not going to cover it today because we think it's a little bit daunting for the first workshop, specifically in workshop 5 when we go through PyTorch. So you would think, I guess, week 6, we will be going through a little bit of math of how this works behind the scenes. So you really understand, you basically really understand what is PyTorch doing? Why do I write this line of code? Why do I do this? And we think that may be helpful, but that will be a future workshop. So with all that in mind, we kind of have a sort of gradient to say update that looks something like this. This is our current weights, right? WK, our weight at time step k. We're saying, okay, let's take our gradient and let's nudge our weight in that direction by a little bit. Maybe not by the entire gradient, but just in the direction of that gradient. And that's why we have this kind of alpha in front. Something called a learning rate. And we'll get to this a little bit later. Why we may have a learning rate and why not just step towards the gradients all the time. And with this kind of update rule, we will get WK plus 1, or our weight, but updated. We just went from time step k to time step k plus 1. Does that make sense what's happening here? Any questions so far about what gradient descent is and why you may see this being, very helpful for trying to train neural networks? We good with that? Okay, cool.
Also, just kind of adding on to this, like we mentioned that PyTorch does it for us and it's a black box. Going off of that, the alpha is something we choose. Like even in PyTorch, we as the user get to choose it, whereas the update rule is kind of baked in to the black box. So it's something that you can decide and also kind of discuss that when we're talking about hyperparameters. So I think that might have been in big, but yeah, kind of good yeah.
Oh, perfect. Learning rate. So basically what the learning rate is, if you think about it, because when we're at a certain point in the loss landscape and we say, okay, let's go into that kind of negative gradient direction, just kind of step downwards. How much should we go, right? In fact, that is a very big problem that has to do with optimization is how do we choose that number? How do we choose something called the learning rate and the rate in which our model is learning, right? In this case, the smaller the learning rates, the slower we converge to a sort of loss minimum. And that can be good. If you look at this example, right, the direction of greatest descent is clearly to go in this direction, right? If we're here, clearly we got to go in this direction, so we're going down. However, if we have too big of a learning rate, we may completely overshot a minimum, and sometimes even diverge. Because in this case, we just converge a little too slowly, right? And that seems fine. But imagine we have something here that kind of goes like this. It just kind of is a very shallow space. We may overshoot this perhaps really valuable, really good local minimum to be somewhere else that is less ideal of a solution. So that is why a lot of times for learning rates, we will actually want to choose something that is below 1, something that is like, don't go the full gradients. Because again, the thing about gradient descent is it's what is called first order method. It only looks at the gradients in its very current states in the loss function. It doesn't know what's ahead of it. It doesn't know, oh, a global minimum is actually like over there. It just knows at this very point, the best way to minimize the loss is to go into that direction. It has no idea what's happening around it. And because of that reason, we sometimes want to actually choose a smaller learning rate to, in a way, more conservative, let our model more conservatively learn, so that we don't kind of, those sort of things doesn't happen. However, if we choose something too small, we may kind of stop at a certain point because our gradient has become so small.
Intuitively, like going off of overshooting and not going the full gradient. Like, for example, let's say we're training on like a lot of images of cars and car identification. Maybe we have like some weird looking car that, just doesn't occur as often. And if we learn the whole gradient for that, it's just going to learn in like a different direction than we actually wanted to learn too. And also to add on learning rate, like when I learned this, I thought a useful way of like, visualizing in my head was kind of like to see how small it is. So like we say it's small and it's smaller than 1 times the gradient, but usually in research and like in industry, it's usually 0.1 or 0.01. Those are the ones that we start off with. And if there's like one-off cases, of course, there's more tuning going on.
Yeah. It's usually smaller than 1 and like a lot smaller, like 0.1, 0.01, 0.001. People choose very small learning rates. And again, that's for a reason. We'll get to it in a little bit.
Just to kind of put it into context.
Exactly. So this is a little simulation. If you go to acm.github.io, which is basically a kind of gradient descent visualizer. And you kind of play around with it and kind of just see the sort of ideal conversions and like overshooting and everything. We think it's a pretty fun kind of interactive little tool for you to get more intuition on what gradient descent is.
Also, shout out to ACM Hack for making this.
Oh yeah.
Yeah, because it's a great like collaboration between us and them, and like also advertising them as well. You can do cool things with software.
Yeah. All right, let's jump back to the slides. Yeah. Okay, cool. So, because of, wait, is that next slide or let me skip the thing? Yeah, okay.
Okay.
So, adding on to gradient descent is something called mini batch gradient descent, or have anyone here heard of something called stochastic gradient descent? Right, SGD, perhaps that's a term that's being thrown around. Now we know what gradient descent is. We kind of have to tackle it like the elephant in the room, the thing that everyone seems to be using, stochastic gradient descent. Does anyone know what the word stochastic means, just on its own? Random, right? So what do you think that random is referring to?
Direction.
Not necessarily. It kind of is part of it. But remember, we have like a mathematical set direction saying we're going in that direction, right?
Just to give like a little more context. So like, let's say we're training something, like we have a lot of data points, and usually gradient descent usually does it in like a random fixed order.
Yeah.
And through all the data points. So just kind of looking at that, what do you think SGD would do if it's just like random? Like where do you think the randomness comes in? Any ideas?
Randomly selects what's being trained.
That is correct. The randomness happens in the selection of data. And we'll talk about what that means here. So here's a kind of the issue with gradient descent is we always have the choice between let's use all the data, right? To calculate a gradient, let's pass in all of our images and let's get out all the outputs of our images. And now we have, kind of loss values for all our images, and you can calculate gradients for every single one of them. And we kind of like average them by the very ends, right? That's something we can do. But the issue is if we put in all the data at the same time, your computer will scream at you and then spontaneously combust. That has happened to me. Well, that doesn't seem very practical, right? Especially with something like machine learning, like even the kind of like a lot of the what I like to call hello world examples of machine learning uses like data sets of like 50,000 or 60,000 images. If you try to pass that into a model, even like a remotely large model at the same time, that's a lot of data, right? Especially when you see later for computing gradients, that's a lot of GPU memory. And does everyone know what a GPU is? Yeah, really, it's a graphics card, and that's kind of where like a lot of machine learning models are trained on, because like half of machine learning is like linear algebra, and the one thing that these GPUs are really good at is linear algebra, because that's also what computer graphics is. The other option is kind of like let's put in one input at a time, right? We kind of just pick one image from the data set, put it in, we get a gradient, update, get another image from data sets, put it in, get the gradient and update. But what is a potential problem with that? We even kind of hinted at it a little bit earlier of why that may potentially be problematic. Any ideas? Yes.
The image you get is like really weird. It just shoots you in the wrong direction.
Absolutely. Outliers, right? Because this is a very data-driven approach, we cannot be sure that our data set will be completely clean. Right? We cannot be sure that our data set doesn't have anything kind of weird here and there, right? If you only take one image at a time, and let's say it happens to be the first image we take, it's just like a little weird, because that image is maybe a little bit abnormal for what we are trying to predict, what we're trying to train, that the resulting gradients may be pointing in the wrong direction. And we tell the model to say, oh, go into that direction. Gradient descent becomes very unstable, because now suddenly we're kind of going all over the place, and it just becomes a lot less effective. So the idea is putting in some inputs at a time, a batch of inputs, if you will. And usually that batch is like a lot smaller than the amount of data we have, hence mini batch gradient descent. So to perform mini batch gradient descent, we need to choose something called hyperparameters. So if you, some machine learning scientists, they call like the actual weights of the model parameters, hence hyperparameters for these things. Basically, hyperparameters control the training process of the model. These are things that we choose, right? Parameters that we tune, and it's not tuned by the model itself. Now, the model tunes the network weight and bias itself, like the things that actually affect how do we take an image as an input and then manipulate it to get our output. Hyperparameters includes things like learning rates, the actual architecture of the network, basically how the network is being set up. What is the batch size we should put in at one side, right? So like, in fact, like the structure, the architecture of our network, like is also a lot of choices of hyperparameters. For example, how do you design your network? How do you pre-process your data, right? What should your network be? All of these are decisions that we have to make, and we have to alter these decisions depending on what has already been trained. We look at the output, 70%, 75% accuracy. We're like, we want better. How can we change this learning rate or change the network architecture so we get something better, right? These are choices that we are making, but we're also parts of this machine learning process, because not only is the machine learning, we are also learning what's going on and trying to alter our decisions of designing the machine learning model alongside it. Does that make sense? Yeah.
Or AI would be too powerful.
Yeah, otherwise AI would. Though there are papers that tries to regularize this. So here's just like a little quick graph of like what happens when you change batch sizes. We go to the next slide, I think. Yeah. So, by the way, a quick thing about batch sizes. When we say like mini batch sizes of like, we only take like some data at a time, feed it through the network, and then we calculate the gradients for every single one of those images, and then we average those gradients to find this sort of average distance. The reason why that's a good choice is because if you think about the idea of having outliers are outliers for a reason, because they're uncommon, right? They only happen like once or twice in like a batch of images. And because of that reason, even if the gradient is pointing in some wrong direction, because we have chosen so much data, when we average all these directions together, we kind of get this almost like master direction, this sort of averaged direction that we can be reasonably sure is what we like to call a good approximation of the direction that we'll be going in if we just feed in the entire network. Right. So and when we say many, we really do mean many. Like, for example, in a network of like 50,000 images, our batch size may be like 128. And like if you increase the batch size to something really big, you actually kind of see the sort of diminishing return where the advantages of having a larger batch size becomes less and less obvious. Right. So I think a good way to think about this is the ideal is that we're feeding in the entire data set every time. So we get the best possible gradient, the best possible direction to go in order to minimize our loss. However, we can't do that because that is too much computational power. So what we try to do is we try to just only take a portion of that data, randomly sample from that data, people. Hence, the randomly sample is where the stochastic comes from. We randomly sample from that data, and we basically say, okay, let's hope when we average those like smaller batch of gradients, it's a good enough approximation of what that big gradient is, what that ideal gradient is. Does that make sense?
Also, to add on that, like not only like dumping like the entire data set and it's too much computational power, it could actually be better to use SGD sometimes and like instead of the whole data set. As like we said, there could be like outliers, and averaging out many batches could like really help with the direction of gradient descent as well.
So this kind of ties into kind of like one of the biggest problems, one of the first problems in kind of computer vision, which is or just machine learning in general, which is supervised learning. And the idea of supervised learning is the data we're used to train our model are pairings of inputs with a corresponding expected output or label. We're supervising the machine directly to say, for this input, we want this output, right? So an example is basically like the hello world of machine learning, of neural networks is the MNIST handwritten digit data sets, and the pairing in this case will consist of like a 28 by 28 image here that corresponds to a label that's refers to what this digit is. And basically you will be trained, let's say like like a machine learning model that basically says, all right, given this image, try to predict that this is 4, this is 1, this is 0, right? Next slide. So in total, MNIST contains 70,000 of these pairings. The first 60,000 make up what we call training sets, which is basically this is the sort of set of data that we what we train the images on. And the remaining 10,000 pairings will make up the testing set, which is basically the set of data that we use to evaluate the model's performance. Why would we want to kind of split our data sets into a training set and a testing set? If we want the best model, why don't we just put everything in? Why would we want to make that sort of splits when we are actually trying to tune a model?
Yeah. Any ideas? Yeah.
Yes.
If you include the testing set in the training set, then it'll memorize everything that's in the testing set.
That is exactly correct.
Yeah. So why would that be a problem?
Because then you don't actually know how well the model's going to work on data that it's never seen before.
Yeah, exactly.
The whole thing about machine learning is we want it to be able to generalize. We want the model to be able to take data as never seen before and make some sort of inference about it, make some sort of conclusion about it, classify it, right? If we put the entire data set in, the model can not directly, but effectively memorize the entire data set, memorize the positions of the pixels, and basically say, when we have this exact pixel combination, that's a 5, something like that. And that's counterproductive because in the real world, like even with something like handwriting, every single handwriting is different. The pixels are going to be slightly different. So when we feed it a model that's maybe just like 1 pixel off, it may not be able to recognize that because it has the term that machine learning scientists like to use as overfits to the training data set, right? So that is why we want to split it into the training set and testing set, is because if we feed the whole thing in, we won't be able to see how it's able to generalize the data as never seen before. Next slide. Yeah, so that's basically we're saying, yeah. So this is kind of what, yeah. Right. However, there's another thing here. Sometimes a portion of the training set, a very small portion typically, but a small portion of a training sample is preserved as what is called a validation set, which we use to fine tune the hyperparameters for our model. Why do you think we would want to separate the validation set and test set? So basically, to kind of recap, we will have kind of three sets. We'll have this really big training sets, a tiny bit of data set for validation, and another tiny bit for testing. Why would we need two of them? Why do we need a validation set and then a testing set? Why don't we just, kind of just train it on a model and test it on a set, change some hyperparameters and keep testing it on a testing set?
So like one way to look at this while thinking about it is hyperparameters, like just as a recap, could include like many values of like the learning rate or like many different architectures and all that. So like taking that into consideration, why would we need like another set of like portioned off data set called the validation set?
Any ideas? Why would we need a separate validation set? Yes.
Make sure you don't tune it to fit just the testing set, and you make sure that it can actually work with other sets as well.
That is absolutely correct. After all, data is data. There may be some sort of underlying pattern in our testing set that if we don't have a validation set and we're just, running, training our model with the entire training set, getting some result and saying, that's not good enough. Let me change the hyperparameter in some way, and then you rerun the model on a training set. The issue is we may, in a way, kind of fit the model to the testing set. Because even though the model has no knowledge of the testing set, we're never feeding the testing set into the model. We as machine learning scientists, we are seeing the effects of the testing set, right? Because we're evaluating on the testing set. We're saying, okay, that didn't do very well. Let me change a few hyperparameters. But we don't want that, because even though the model isn't being directly affected by the testing set, because we are affecting the model and we are affected by a testing set, the testing set is in a way still affecting the model. And that's problematic, and we don't want that. It's kind of like saying you have a sort of exam to evaluate performance. I give you the final exam, you do it once, you get your score back, and I say, okay, do it again, right? That doesn't seem to make a lot of sense. So the validation set is basically a data set where instead of testing on the testing set, we say, okay, while we're tuning the model, while we're altering the hyperparameters, the results that we're seeing is actually of the validation set, right? Let's say we get like a 75% accuracy on the validation set. We're like, okay, maybe I'll, tune down the learning rate by, a few percent, and I run it again, and I see an improvement in the validation sets. I'll be like, oh, that's good, right? Then after we have done that whole process, we take the model, we test it on the testing sets, and after we tested it on the testing set, that's our final score. We shouldn't try to tune the model any further. And that's what a lot of machine learning papers do. It's kind of like a final exam, whereas the validation set you can see as practice final exams. Does it make sense why we're kind of making that distinction, almost separating the validation set and testing sets? I'm hoping that's clear.
Just to summarize it, so like we first train the model with like different hyperparameters, and then we use like a validation set to see like which of these hyperparameters works best for us. And then after that, we just kind of use the best of those like models, and then we just kind of evaluate it on the test, just to kind of summarize it.
Yes, continue. Yeah. So to kind of summarize, with many batch gradient descent, this is what one epoch would look like, right? We kind of we feed forward the values of the inputs of every single sample in the batch. We calculate the weights and biases, partials to loss function, aka we calculate the gradients, and we say, okay, we take the average of that gradient, and let's say nudge the model weights in that direction. And we do that iteratively. We do that many times. A lot of times, tens of thousands of times, tens of thousands of iterations. And at some point, hopefully, that will converge into some sort of good local minimum that gets us a relatively low loss and effectively a decently high accuracy. So that's kind of like the pipeline, or like the kind of training process of many batch gradient descents, or as some of you may know as stochastic gradient descents. Yes.
Just a question. So compared to giving it one single image or input at a time, so many the unit batch gradient descent, update the weights every m inputs instead of like every one inputs.
Yes, that is correct. Because you're feeding in n inputs at a time, right? So you're kind of computing the average gradient every n inputs. Because you're kind of doing it all at the same time.
Clarify what pops like one whole iteration through the data set.
So like there's kind of two separate approaches to stochastic gradient descent. Some people like to just kind of sample the data set a bunch of times and it just kind of goes on for some number of iterations. But sometimes it's rather easier to just kind of take the whole data set, randomly shuffle this data set and just say, okay, the first 128, the second 128, and just kind of slowly make your way through the data sets. And we have made your way through the entire data set. We call that one epoch. So that's just kind of terminology. So you may see us throwing that word around, but that's
Why we have it on here.
Yeah.
But
okay. Before we get to neural networks, oh wait, actually, it's time right now. 7:50. I think we can continue with a little bit of networks overview. Yeah, next slide. So neural networks is kind of like the bread and butter of machine learning nowadays. It's because it's kind of like the basis of like, this is the thing, right? This is the weights and biases that we'll be learning. This is how we're going to take some inputs, manipulate it in some way, and then get some sort of output. And you may have seen illustrations like these being thrown around all the time, but you may have wondered, what does this mean exactly? So the idea is, okay, so what we have here is a neuron, right? And basically with neurons, we have this sort of expression here called logistic regression. And what it is we take some sort of number of inputs, it can be of an image, and we basically say for every single one of these inputs, let's weigh it some number of amounts, weights, right? Let's weigh it some number of amounts. And then let's add it together. We take that result of addition, we pass it through a sigmoid function to basically normalize it between 0 and 1. And that would be our neuron, right? It kind of models after how the brain works, where we have multiple inputs into one neuron, and the neuron either activates or it doesn't activate. Next slide. And again, just a little kind of recap of what the activation function is. It is a measure of how kind of positive the relevance weighted sums is. So basically, again, it's just kind of this idea of like we're kind of normalizing it between 1 and 0. Next slide. So the difference between kind of so then we have this kind of distinction of logistic regression and kind of like single layer neural networks, where the difference is we have an addition of a bias, right? Because at the very end of this kind of like, let's do this kind of pairwise multiplication and let's add them all together. We add a bias because we want this kind of additional term to be able to, it's an additional thing to learn. But if you think about logistic regression as a kind of like a decision boundary, it allows us to shift this decision boundary around such that it is not anchored at the origin, which can be very helpful sometimes.
also, just to add on everything we said, like even weights can be related to like what you learned before, like linear regression also had weights for features, similar to like, neural networks as well, perceptrons or neurons. And same with the bias, like when you take a line, you can shift it around. And if you don't have like a plus b term in ax plus b, it just like stays at the origin and scales. Right.
Okay, so this is kind of like the whole like pipeline of like what it means to be training for a single input. We first have to define an architecture, either it's fully connected CNN or RNN. We determine a number of inputs, hidden layers, and outputs. We initialize weights and biases. We feed forward our images through this network to get some sort of output and compute the loss. We determine that loss, the output error, and we do something called back propagation. We basically take that output and we say, okay, let's compute the gradients with that. And let's update the weights and biases using gradient. And we kind of do this a bunch of times. These 4 steps a bunch of times. Next. And yeah, but before we start to do the Kahoots, let's have a 5-minute break. Kind of just so you can walk around, have a drink of water, and I think we have a little Kahoot prepared. So yeah. Thanks for coming to the first part. We hope to see you 5 minutes later.
Lazy.
The music? Go with that. I don't know if you're sharing the music, but we can. One thing, 1 second. I can fix this. Oh, okay. Don't worry about it. I can fix this. There we go. There we go. Kind of join by this link. It's very similar, just a little refresher of what we have talked about for the past hour or so.
You want to join?
You can't have it played.
Change
I can know
the last Friday.
It's fine. Like, what do I?
Yeah, you can imagine.
Raise your hand if you still have not joined or don't, unless you don't intend joining, which is totally fine. Raise your hand if you are still trying to join. Okay. Okay, cool. That's everyone. All right, let's start.
Oh, he's kind of curious.
The internet loads. Okay, cool. All right. Questions are pretty simple. For this week, they'll slowly wrap up next week, but yeah. So this is kind of just like okay. So this is kind of part of what we like to call the ethics revolution throughout ACM. We're trying to talk more about ethics in every single subcommittee, and we're going to be starting to do this next week, where we have a little discussion on why it's important. Oh, there we go. Hopefully this one's pretty obvious. It's one of those questions that's just trying to get you to complete as quickly as possible. But 6, 7. Yeah. That size has very fast internet. Oh, which is fun. What is MNIST? We kind of talked about this quickly.
Okay.
Oh, yeah. Yes, it is indeed a database of hands and digits from 0 to 9, in fact, and we may be dealing with that for projects. Okay. Slowly moving on. Parameters. Amazing. This is the kind of difference of what hyperparameters are. Is the model doesn't learn the hyperparameters. We are the one who decides what the hyperparameters are. And if you can think about this in an almost like I don't know, like transhumanistic way, we are the ones who are learning the hyperparameters. We are part of the machine learning model. Not really, but it is the parameters that are actually provided by the users, right? So we look at the outputs and we say, how can we change the hyperparameters so that the model performs a little bit better? Oh, Egger. Favorite professor. All right. I need to cut that part out. Multi-site. Oh, what are examples of hyperparameters?
So you could choose like multiple.
Yes.
That's why it's multiple. Oh my gosh.
That was so weird. Wait, devices are changed because maybe not great. Let's go.
Oh, okay. Very good. So weights and biases are the actual parameters inside the model that we use gradient descent to learn. That is what we're nudging around in order to get the minimum loss, right? And with learning on a number of hidden layers, that's something we decide. Number of hidden layers basically is what does the neural network actually look like, and learning rate is how fast we're learning. Gradient descent. That's really good. Okay. Slight change near the bottom of the leaderboard. What's the structure of a neural network? So you remember kind of like did we ever explicitly state this? But like we kept rambling about it. It should be okay, amazing. We have a unanimous answer. Yes, we go from input layers, something that's happening in the middle, that the model is doing things to the output layer that we eventually be applying the loss to and trying to do gradient descent. This kind of. So what does this represent? Oh, the image will pop up.
Wait here a second.
Single name.
Okay, so this is a perceptron / logistic regression because if you think about it, it only had one layer, right? We went from the image with a bit of slight multiplication and addition, we went straight to the outputs. So with that in mind, errors being pretty good. Why do we have a separate test set? Honestly, let's just have a separate test separate. Yes, to prevent the model from only memorizing the data. I don't think this is a question, so I'm going to ask it just as an extension. Why does anyone remember why we have a validation sets? Kind of like as kind of just like separated out from the test set, training set. Does anyone remember? Is that the next question? It's not the next question. Yes.
So we don't just like manually just hyperparameters to pass the test set?
Exactly, right? We want to basically make sure that we're not like the model is truly seeing unseen data. The model isn't seeing data through us, right? Errors are pretty good. What's the number of epochs represents? Yeah, we did. Yeah, we did. Why do we get Ooh, okay. Number of groups you break the data into. So that is kind of like just like a mathematical thing where like if you divide by the total number of images in the data set by our map size, that's what you will get. It is the number of times the model will train on the entire data sets, right? Because if you iterate through the entire data set once, that's one epoch. It's kind of just a convenient way to say a bunch of iterations. Given some map size. They're doing really good. Anyone can What is supervised learning? Again, term we around here and there. Does everyone know what K-NNs are? It was covered in beginner track, but just
K-nearest neighbors.
yeah, K-nearest neighbors.
Oh, this is the last question.
I will very quickly mention it. Right. Okay. So supervised learning is when we're training models, when we have a data sets that have some sort of inputs and output that where we're saying this is what we want the output of the model to be. Right. We're supervising. We're supervising a model. When we're training a model without labels, that is something called unsupervised learning. We want the models to discover patterns on its own without any sort of predetermined labels.
The red and green are the same, by the way.
Yeah, the red and the green are actually the same. KNNs are something called K-nearest neighbors, and it's kind of it's like half supervised. It's semi-supervised.
You could do
It's kind of semi-supervised, but it's not the entirety of supervised learning. It's something called, it does something called clustering, which basically says if you kind of plot all the data out, similar data will be grouped in one class. There are many KN algorithms, so all right, we have the podium. One neuron. Very good. Ooh, shit. Oh. Back size. There we go. Yeah. So 1 neuron, Paul Eggert himself, for legal reasons, that's a joke. And I guess those of you who are in podium, come to us later. We forgot to prepare prizes today, but we just want to like note your names down so we can give you something next time. You know, we have snacks. The CS department finally approved our budget, so now we have to use it somewhere, right? So that's what we're giving out prizes. But yeah, 87% correct. I think that's pretty good. You guys have been listening. That's awesome. Let's kind of move on to the second half / second last third of our of workshop number 1, with something called for propagation, and it kind of slightly more detail. When we take an image and put it through the neural network, it's doing stuff to it and it gets an output. What's the stuff that it's doing? What's the math there? I know you guys love math. Right, so we've got some inputs. How do we manipulate these inputs so that you arrive at some outputs? For example, scores or probabilities that the output, say, belongs to a certain class. Wait, anyone have any ideas of the sort of area of math that is kind of very integral to this process? Some of you may have taken this, some of you may have not. But it is some major requirements for the CS / math majors in here. 3A. What is that class called? Linear algebra. President? Linear algebra. This is our favorite topic. If you're doing machine learning, you'll be dealing with this quite a lot because that's kind of like half of machine learning. And you will kind of see why that's the case in a little bit. So let's revisit logistic regression again, right? So we have some sort of inputs, and each input is kind of like a separate dimension. We can think of it as a vector with x1, x2, and x3. What we're really doing is we're saying, okay, let's take these inputs. We do kind of this sort of pairwise multiplication, W1 times x1, W2 times x2, W3 times x3, and the results of those, we add them together, right? This can be represented by, like W transpose times x, or like something called a dot product. Has everyone heard of what a dot product is? Has anyone here not heard of a dot product and is kind of confused? Right, that's totally fine. Basically, what a dot product is let's say you're taking the dot product of these two vectors. All it's saying is just saying x1 times w1. You do multiplication, 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 and the results of those products, you add them together. Right.
And that's also the multiplication represented here.
Yeah.
And the transpose is actually to make the dimensions like match up.
Yeah.
For multiplication.
So that's just kind of to make the matrix multiplication make sense. Yeah. It's really just another way to
just to review, transpose is just like taking the rows and columns and
and at the very end, we add a sort of like scalar bias to get some sort of output / activation. Yeah, like obviously sometimes we'll put like brackets around it and put a sig point or something, but that's not terribly important here. So this is a single layer example. But what if we want to have multiple outputs? What if instead of just classifying true or false, we want to say is it class 1 or the class 2 or the class 3, right? And like a lot of times, what a lot of machine learning textbooks and whatever, they'll kind of give you this as just kind of like a big old like matrix multiplication. But really what is happening is we're basically doing this previous process of doing this kind of pairwise multiplication, adding it together with a bit of bias. We're just doing it 3 times, right? Or we're doing it how many number of output classes, number of times. If you think about it, we can have this going on. We do this once and we get this output. We do this a second time and we get this output. And we do it a third time and we get this output. Does it make sense what's happening? So it's almost like there are 3 separate models that's going on, but we're kind of merging it into one big one. And that's kind of how we will have multiple outputs. Yes.
So each neuron has its own set of weights for the inputs.
You can think of it like that, though in practice it's just one big matrix that we're looking at. It's just very helpful to think of it as kind of like 3 separate things that we're doing here.
Right, and also this is like We haven't really gone over it too much, but this is like a fully connected like layout. We'll go over this later. So like if you're confused, don't worry about it. But not all of these neurons from the previous layer to the next layer need to have like a weight associated with it for the calculation. So
Yeah, exactly.
putting it out there.
And if you think about it, it's just like multiplication, 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 sum, add a bias, multiplication, 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 sum, add the bias, multiplication, 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 sum, add the bias. We're doing it 3 times. Yes.
So I'm just like looking back at like the activation function. So
Yeah.
like it has a specific range of X values or inputs.
Right.
That you have to provide for it to like even be a valid like activation between that function. So is a bias like a way to like kind of like standardize the output between like W3 and X so that
You can definitely think of it that way. That is something that a bias can definitely do.
Also, going
yeah.
on your question, that's probably because we haven't applied the sigmoid yet.
Yeah.
Um,
And another thing is we're not applying the sigmoid here because like we're just like we're trying to show you the like this part of it, right? But like sigmoid doesn't really have a limited range. It takes input values all the way from -infinity to infinity, and it kind of like maps it to between 0 and 1. Does that make sense?
These will eventually be mapped when we add like a so it'd be sigmoid of this expression.
but just to, like go on top of that like
Right.
I feel like in the graph that we have here like it's kind of like approaching 1 as it approaches positive infinity.
Yeah.
So like if we have like inputs that are like greater towards positive infinity, like would they just be like how would we be able to find like a correlation out of that?
Right, and they will all get like switched to 1, right? So that's kind of why the bias is there. Is so like we're kind of like, all right, let's move you to be centered around back to 0 again. But again, it's something that the machine will learn. Like it's not something that we intuitively go and do on our own, right? And there are definitely techniques that we'll cover later, like batch normalization, that basically we'll be able to say, okay, if things are getting too big, let's kind of just squish them, it's like a deterministic way of normalizing everything. So there are definitely techniques to kind of prevent that from happening, right? And also just different activation functions that doesn't have that property of squishing everything when it's really big.
Like we'll also talk about ReLU, for example, as
Yeah.
another one. But the sigmoid should deal with what you were asking.
Yeah. Okay, so this is where the linear algebra comes in. Because to try to represent what's happening here, we can use something called a matrix multiplication, right? If you think about like with the W1 transpose, W2 transpose, W3 transpose, they're really just like the weight vectors of the W transpose X, so the dot product that's happening, right? If you think about multiplying this matrix with our X over here, what we're basically saying is just we're saying this dot product, we just kept doing this, right? So that's why we kind of have this like WX plus B formation here. We have a matrix times a vector plus a bias equals to our final activation. So that's why you will see a lot of matrices in machine learning, is because it is just a really convenient way for us to express, all right, all these like dot products and whatever, let's put them into one big expression, one nice and clean expression. And we can honestly do quite a bit of math too. Does that make sense so far? Like why we may be dealing with matrices? Anyone confused? Like, I'm not terribly like again, just raise your hand and ask us to reiterate if you want.
Yeah, also anything with the slide like the notation or something that if go for it, because there's a lot of numbers and letters. So
It's a lot of numbers. It's a lot to take in, right? And like we don't expect you to be able to just like write out these equations by memorizing them, because again, like let's be honest, PyTorch does a lot of this for us, right? Like you'll be able to just put in the input number, the output number, and just kind of does everything. But yes,
So in the first step,
Yeah.
is the other weights and biases like random?
oh yes, they are usually randomly initialized. Some people initialize them to 0, and like the whole thing with weight initialization is actually the whole field of research is how do we initialize weights so that we kind of give our model the best chance. And in fact, like even nowadays, we'll see new papers that talk about, oh, here's a better way to initialize weights. And honestly, studying weight initialization is mostly actually statistics. There's definitely a very like a complete different way of looking at neural network models that is a lot more statistical than how we're looking at it currently.
also there's usually not like a set way to do it. It could also depend on your problem.
Oh yeah, it definitely depends on your problem, what your layer actually is. Like, is it a convolutional layer? Is it a dense layer? What you want your output to be, et cetera, et cetera. Yeah. So with that in mind, let's try to formalize it and put it into a little bit more math. And again, this may be a little bit daunting, but like this is something that we kind of have to go through to kind of build that intuition and build that confidence eventually when you actually put this into code. So
Yeah, so actually when I start off with this slide, I think like the last slide is actually pretty good. So I'll go on that. So that's just a little bit of notation. So you see like there's like 3 numbers on there with the W. So the first one represents the current layer. So we want to actually do this neuron. So that would be the 2, the second neuron, and the third layer. The third 3 is the superscript. And 4 would be this neuron. So just putting that like all together, when it says L, W to the L, J, K, that means the weight from the Kth neuron. So this would be K, so K is 4, and J would be 2, so to the J neuron, and the Lth layer would be. And that's, so before we go any further, just kind of like to put this in context to what we learned, nothing actually new. If we look at it here, so this would be writing this back. So if we have like the set of activations here, we would have W11, A11, W12, A21, I think, and then W13 and so on. So that would just be the previous layer to the, or sorry, the current layer to the next layer. So are there any questions on this?
It's like the idea of like extending the previous slide is just
Yeah.
like, what if we take the outputs and we just
Right.
like made an input of a new layer, right?
It's just
And-
new notation, yeah.
That's how neural networks get deeper. And that's why you may be hearing terms like deep learning. It's because when it is not just one shallow layer.
Oh,
Yes.
sorry. Yeah, I just had a question. So like, for each input, like we're doing like a WX plus B in, and when it goes into the second layer, you're getting the result, which is the A from those 3 inputs in this diagram. So after we get that, can you just explain like what we do after that? I guess that's probably the next slide, but
Yeah. But like basically take that and that's you treat it as like your new X, if you will.
okay.
And you do it again with new weights. And that's kind of how you have a bunch of different layers. Yeah.
So yeah, this is like basically the last slide, but this is just referring to activation and the bias. And yeah, that's pretty much it. The superscript and the subscript are just like representing the layer number and the neuron number. See what that. So layer 2, neuron 3, layer 3, neuron. But yeah, so this
This is
would
much notational stuff.
right. So this actually relates back to your question. So the mapping of like numbers that are like not 0, 1 to something that is 0 to 1, that's what sigmoid does. So the sigmoid of the calculation we talked about before, the sigmas are just adding the numbers and the weights up. So like the matrix multiplication that we talked about before, and the bias, like he said, could like normalize things and shift it more to like the upper range you want. So this is basically the notation, the same notation we talked about, touched on. But is there anything that anyone has questions on this equation? They're just a matrix multiplication, just written out like sigma notation.
Yeah, this is really just dot products if you're wondering.
So, all good. And this is just a continuation of the same thing. So like, I'll just go over this box because it might make it better intuitively. But all we're doing is we're taking the second, we're trying to get the activation for this neuron. So all we're doing is we're taking the first layers, all of the first layers neurons, and then this is referring to the first layers weights, but then the K would be the different neurons and adding it to the bias of this neuron as well. Again, going off of the double. Right, so this would be similar, except we're just covering that this is like a J by K meter. So just to say what J and K are, J is the current layer number of neurons, and K would be the previous layer number of neurons, which is counterintuitive. I don't know why we did that, but
the reason why we do that is because just like the core matrix multiplication.
Right.
If you think about it like J and K, like if our current layer has like a dimension of K, when we do the multiplication, we actually get a sort of like J times 1 sort of dimension. So that is why we kind of have like, our outputs here and our inputs here.
Yeah, so like going off of that, it's because like J is the number of neurons in the current layer, right? And K would be the previous layer, but we have J by 1, or sorry, K by 1. So then it would be J times 1. We'll also see that in the next slide as well. Yeah, so this is also another way to look at it. So the previous activation is a K by 1 vector. So the previous number of neurons times 1 would be the dimension, and B by L would be J by 1, which is the current number of neurons in the current layer we're looking at. And this would be the number of activation. So these have to be the same because we're adding these two vectors together. And just a slide with all this like really visualized, but next slide or so. Yeah, it might be. Yeah, so this is okay. ZL is just another way of saying the J by 1 weighted input vector. Yeah, this is also similar. But yeah, so this is what I was talking about. So as I think my head's covering this, but these are this is the bias vector. So the BL, and this would be the weights vector, and this would be the AL minus 1. So that would be like the previous layer. And yeah. So do you guys have any questions on how this really works?
Does everyone remember how matrix multiplication works? I'm just going to throw that out there because it's not something that we just remember like willy-nilly. Like it's fine if you don't remember because it's not something that we.
I mean, just going over it quickly, it's rows and columns. So like WL11 times AL minus 1 plus this times this plus this times this.
So you can kind of think of it as like you do this, work your way, sum, that's your first value. And you're just like you're kind of taking the dot products. That's why dot products are useful. Of this little thing with this little thing. This little thing, this little thing. And you're kind of seeing how like, oh, it's actually kind of like just 3 separate WX plus B that's going on.
And just to check your answer, it'd be 3 by 5 and a 5 by 1. So that would be 3 by 1.
Yes.
And they should match up.
So in this case, we're kind of taking this sort of 5-layer neuron or like 5-layer activation. We're saying, all right, let's transform it into a 3-layer activation with this matrix.
So this would be the previous layer and the weights associated with all the neurons for that layer to the. So yep. Also, a question to test your understanding. So how many neurons would be in the current layer L?
So like after we have applied this, what is the dimension of the vector that we're going to be in?
There's a lot of hints, but
yes.
3 times 1.
3 times 1. That's exactly correct because we're going from 5 to 3. Yeah.
How about L minus 1?
What is the number of? All right. 5, right? Because we went from 5 to 3 again. Yeah.
Okay, so the feed forwarding process is basically what we went over, except like just kind of named. So we compute the result for all of the layers. So that's why it says L is 2, 3, and so on to big L. It just means all of the layers that we have. And the big L refers to the output layer because at the end, of course, we do the same thing, but we output the result. And this would be the equation for it. We kind of covered it in little steps, but if you have like any questions on this part, I'd be happy to.
And just kind of like a sort of idea to kind of visualize what's really going on. You can think of the feed forward process as saying we take in, again, like I like to use the example of images because it's very helpful. Let's say we're taking like a 32 by 32 image. That's like, I don't know, like 10,024, right? We have this kind of 10,024 dimensional vector. And we're basically saying via matrix multiplications, we're able to kind of reshape it into vectors of different sizes, continuously. Let's say, our second layer is like 100 neurons in size. Then we take this vector, multiply it by a 100 times 1024 matrix. We make it into some other shape. And basically through a bunch of matrix multiplications and also biases, keep reshaping it into different sizes until we reach some sort of end, some sort of output by the very, very ends. In this case, if we have, let's say, a classification task of like trying to classify this image into 10 different classes, right? You know, dogs, cats, airplanes, cars, whatever. That's an actual data set, by the way. Then we will have by the very end, a 10 by 1 vector. Right, and each and every single one of the channels will kind of correspond to, if you will, the probability that this image belongs to this class, and the final prediction will be the class with the highest probability. So that's really what the feed forward is. It's just kind of taking this input vector, just keep transforming it in some way such that we reach the very, very ends. And because it is really just transformations that we very clearly know what's mathematically going on, and we know the gradients of, there's actually a way for us to back propagate, go from the very output, so from the loss, back propagate and calculate the gradients until the very, very end, which we'll cover in week 5.
Yeah, so that's how we like optimize our weights to get ideally.
Yeah.
And yeah, so this is
Yeah, we covered all of this.
so I guess we're like
Yeah.
but
We're basically finished.
Yeah.
But just like a quick ethics slides, basically saying we're going to be talking about stuff in the future. And conda environment setup, extremely optional, by the way. You probably don't at all need this. We're not going to teach this. But basically, conda is a way for basically Pythons to do package management. And again, if none of those words are in the Bible for you, we won't put them in the Bible in just a few workshops.
also it's perfectly fine if you use Colab because we're probably going to be doing it.
Yeah, we're going to be doing a collab. But like, just kind of putting the idea of conda in your radar, because if you continue to go on projects track, you're going to be seeing this, right? But I think besides that, there's some resources here. Again, you can see them in the slides.
If you are like interested in anything we talked about,
Yes,
be sure to
the background theory and math. Again, we're going to go on.
yeah, this is like kind of what we didn't cover.
Yeah. Yeah. Any final questions before we go?
But,
Thanks for coming to the first workshop.
and even though the feedback form is not present here, please do fill out the feedback.
It's all the way at the very end. Yeah, thank you for coming. We hope to see you here next time.